Artificial intelligence agents are entities designed to perceive their environment, reason about it, and act in pursuit of defined goals. They are not simply passive models that generate outputs when prompted, but active systems that structure intelligence into purposeful behavior. The distinction between a raw model and an agent is critical. A model can generate text, classify images, or predict outcomes, but it does not have goals or autonomy. An agent wraps intelligence in a framework of objectives, context, and actions. This makes agents the practical embodiment of AI in real-world applications. When we talk about agents, we are talking about systems that can operate continuously, adapt to changing conditions, and pursue objectives over time, rather than one-off computations. At the simplest level, an agent senses and acts. It receives inputs from its environment, processes them, and produces outputs that affect the environment. In AI, inputs may be text, images, audio, sensor readings, or structured data. Outputs may be dialogue responses, commands to software systems, or physical actions in robotics. The agent's behavior is guided by policies, rules, or learned models. Its goal is to maximize some measure of success, whether that is solving a problem, satisfying a user, or optimizing a reward function. This cycle of perception, reasoning, and action defines agent behavior. The agent is not just reacting blindly, but is structured to pursue objectives, even if those objectives are simple. Rational agents are a useful framework. A rational agent is one that takes actions expected to maximize its performance measure, given the information it has. Rationality is bounded by limitations of computation, data, and uncertainty. Agents must make decisions under incomplete information and limited resources. This makes them realistic and applicable to real-world scenarios, where perfect knowledge is impossible. Rationality does not mean perfection, but consistency with goals and knowledge. For example, a trading agent in finance may not know the future of the market, but it acts rationally by using available data to maximize expected profit. A healthcare agent may not know every detail of a patient's condition, but it acts rationally by recommending treatments consistent with guidelines and evidence. Architectures of agents vary. Reactive agents respond directly to stimuli without internal models. They are simple and fast but limited in reasoning. Deliberative agents maintain internal representations of the world and plan actions. They can reason about consequences and adapt to complex environments. Hybrid agents combine reactive and deliberative components, balancing speed and reasoning. For example, a robotic agent might use reactive mechanisms for obstacle avoidance and deliberative planning for navigation. This combination allows agents to handle both immediate and long-term challenges. The belief desire intention framework provides structured models of agent reasoning. Beliefs represent information about the world. Desires represent goals. Intentions represent commitments to actions. The agent reasons about its beliefs, selects desires, and commits to intentions. This framework captures the complexity of human-like reasoning and provides a basis for designing agents that act coherently. Reinforcement learning provides another framework, modeling agents as entities that interact with environments, take actions, and receive rewards. The agent's goal is to maximize cumulative reward. This framework captures the essence of agent behavior and provides algorithms for optimizing policies. Reinforcement learning algorithms, such as Q-learning or policy gradients, provide methods for optimizing agent policies. Deep reinforcement learning combines neural networks with reinforcement learning, enabling agents to handle complex environments. This has led to breakthroughs in games, robotics, and autonomous systems. For example, agents trained with reinforcement learning have achieved superhuman performance in games like Go and StarCraft, demonstrating the power of this framework. Utilization of agents spans many domains. In healthcare, agents support clinicians by retrieving guidelines, analyzing patient data, and suggesting treatments. In finance, agents monitor markets, analyze risks, and execute trades. In education, agents act as tutors, adapting explanations to student needs. In robotics, agents control machines, integrating perception and action. In customer support, agents handle queries, retrieve information, and provide assistance. In personal productivity, agents manage schedules, draft documents, and automate workflows. Each of these applications involves agents that sense, reason, and act in ways tailored to their domains. The versatility of agents makes them central to modern AI utilization. The mechanics of agent utilization involve perception, reasoning, action, and learning. Perception involves processing inputs, whether text, images, or sensor data. Reasoning involves applying models, rules, or policies to interpret the situation. Action involves producing outputs that affect the environment. Learning involves updating models or policies based on feedback, improving performance over time. This cycle defines agent behavior and enables adaptation. Agents that can learn continuously are particularly powerful, as they can adapt to changing environments and improve over time. Agents can be autonomous or semi-autonomous. Autonomous agents operate independently, making decisions without human intervention. Semi-autonomous agents collaborate with humans, providing suggestions or assistance while leaving final decisions to users. The degree of autonomy depends on the application and risks involved. In high-stakes domains like medicine or law, semi-autonomy is often preferred, ensuring human oversight. In low-stakes domains like entertainment or personal productivity, autonomy may be acceptable. Designing the right level of autonomy is a key challenge. Too much autonomy can be risky, while too little can limit usefulness. Balancing autonomy and oversight is essential. Integration with external tools expands agent capabilities. Agents often need to access databases, APIs, or devices. This requires interfaces that allow agents to retrieve information, execute commands, and control hardware. For example, a productivity agent might integrate with email, calendars, and task managers. A healthcare agent might integrate with electronic health records and diagnostic tools. A robotic agent might integrate with sensors and actuators. Integration allows agents to act beyond their internal models and connect intelligence with real systems. This makes agents practical and useful in real-world applications. Learning in agents can be supervised, unsupervised, or reinforcement-based. Supervised learning involves training agents on labeled data, teaching them to map inputs to outputs. Unsupervised learning involves discovering patterns in data without labels. Reinforcement learning involves training agents through trial and error, using rewards to guide behavior. Each approach has strengths and limitations. Agents often combine these approaches, using supervised learning for perception, unsupervised learning for representation, and reinforcement learning for action. This combination allows agents to handle complex tasks and adapt to diverse environments. Reinforcement learning is particularly relevant because it models the cycle of perception, action, and reward. An agent interacts with an environment, takes actions, and receives rewards. The agent's goal is to maximize cumulative reward. Reinforcement learning algorithms, such as Q-learning or policy gradients, provide methods for optimizing agent policies. Deep reinforcement learning combines neural networks with reinforcement learning, enabling agents to handle complex environments. This has led to breakthroughs in games, robotics, and autonomous systems. For example, agents trained with reinforcement learning have achieved superhuman performance in games like Go and StarCraft, demonstrating the power of this framework. Agents face challenges of uncertainty and partial observability. Environments are often noisy and incomplete. Agents must make decisions with limited information. This requires probabilistic reasoning, Bayesian inference, and robust policies. Agents must also handle exploration and exploitation. Exploration involves trying new actions to discover better strategies. Exploitation involves using known strategies to maximize reward. Balancing exploration and exploitation is a central challenge. Too much exploration wastes resources, while too much exploitation limits discovery. Agents must find the right balance to optimize performance. Ethical considerations are central. Agents may affect human lives, raising questions of safety, fairness, and accountability. In healthcare, agents must avoid harmful recommendations. In finance, agents must avoid manipulative behavior. In education, agents must avoid bias in tutoring. In customer support, agents must respect privacy. Designing ethical agents requires careful consideration of data, policies, and oversight. Transparency is important, allowing users to understand agent behavior. Accountability is essential, ensuring humans remain responsible. Governance frameworks are needed to regulate agent deployment. Without ethics, agents risk causing harm or losing trust.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.